In the rapidly evolving field of artificial intelligence, large language models, or LLMs, have transformed how we handle information retrieval and response generation. These models, like those powering chatbots and search engines, pull from vast internal knowledge bases to generate answers. However, when we augment them with external information through techniques like retrieval-augmented generation, or RAG, conflicts can arise between what the model already knows and what it retrieves from outside sources. These knowledge conflicts stem from several sources. For instance, the external information might contain misinformation, be biased due to its origin, or simply be outdated. On the other hand, the LLM itself could have inherent biases or obsolete knowledge baked in from its training data, which might not have been updated in real time. This mismatch leads to unreliable responses, where the model might generate answers that are inconsistent, biased, or just plain wrong. As a result, decision-making based on these responses becomes uncertain and risky, especially in critical applications like healthcare, law, or finance. Researchers from Nankai University, Heihe Lab, Meta AI, and InnoPeak Technology have delved into this problem in their paper titled, "Accommodate Knowledge Conflicts in Retrieval-Augmented LLMs Towards Reliable Response Generation in the Wild." They examine how LLMs handle these conflicts from an information-theoretic perspective, which is a way of analyzing information processing using concepts from information theory, like entropy and uncertainty. The key insight from their analysis is that LLMs behave differently based on how clear the differences are between conflicting and supplementary information. When the disparity is significant, for example, if the external information strongly contradicts the internal knowledge in a straightforward way, the LLMs tend to confidently settle on a preference. They might favor the external source if it's more convincing or stick to their internal memory if it's robust. However, when the differences are ambiguous or subtle, the models experience heightened uncertainty, leading to less reliable outputs. Building on this, the researchers propose a novel framework called Swin-VIB. This stands for Swin Variational Information Bottleneck, and it's designed to integrate a pipeline of variational information bottleneck models. In simple terms, the variational information bottleneck is a technique that helps models focus on the most relevant information while discarding noise, by compressing data in a way that maximizes useful signals. Swin-VIB works by adaptively augmenting the retrieved information and guiding the LLM's preferences during response generation. Here's how it breaks down. First, it processes the retrieved external data through these bottleneck models to filter out irrelevant or conflicting parts, making the information more aligned with the LLM's internal knowledge. Then, it adaptively adjusts how the LLM weighs different sources of information based on their reliability and context. This means the system can dynamically decide whether to prioritize internal memory or external inputs, reducing uncertainty and improving overall response quality. To validate their approach, the team conducted extensive experiments across several tasks. They tested on single-choice questions, open-ended question-answering scenarios, and full retrieval-augmented generation setups. Their results not only confirmed the theoretical findings about how LLMs handle conflicts but also demonstrated significant improvements with Swin-VIB. For instance, in single-choice tasks, Swin-VIB improved accuracy by at least 7.54% compared to competitive baselines. This means that when users ask straightforward questions with clear options, the model is much better at picking the right answer without getting tripped up by conflicts. In open-ended QA, the framework helped generate more coherent and factually sound responses, while in RAG tasks, it enhanced the overall reliability by minimizing hallucinations, those instances where the model makes up information. The paper categorizes this work under CCS concepts in information systems. Specifically, question answering and keywords include reliable response generation, retrieval-augmented LLMs, knowledge conflicts, preference adaptation, and variational information bottleneck. The authors highlight that existing methods often rely on heuristic guidelines without a solid theoretical foundation, which is what their information-theoretic approach addresses. In their introduction, they note that while LLMs have revolutionized RAG by allowing more flexible information access, they still struggle with hallucinations and knowledge synchronization. For example, Figure 1 in the paper illustrates a typical knowledge conflict scenario, showing how discrepancies between internal and external sources can lead to uncertain responses. Regarding how LLMs resolve conflicts, the paper reviews conflicting views from prior research. Some studies suggest LLMs prioritize external context, especially if it's coherent, while others argue they stick to internal memory when it's strong. For instance, one finding is that LLMs might resist external evidence if their internal priors are firmly established, but they'll incorporate it if the external information is convincing. Another point is that LLMs can be overly stubborn, clinging to flawed internal knowledge despite better external data. The authors point out that because LLMs operate as black boxes, understanding their internal mechanisms is challenging, which makes empirical approaches like theirs essential. They emphasize that without a unifying framework, it's hard to consistently improve reliability in real-world applications. Swin-VIB's innovation lies in its pipeline of models, which adaptively augments information by applying variational techniques to balance compression and relevance. This ensures that the LLM doesn't overwhelm with too much data or ignore critical conflicts. In experiments, they used datasets for QA and RAG, measuring metrics like accuracy, coherence, and uncertainty levels, showing consistent gains. Overall, this work advances the field by providing a theoretical lens and a practical tool to make retrieval-augmented LLMs more trustworthy, paving the way for safer and more effective AI-driven information systems.